Okay. Um, so today what we will do is we will go through the whole mass operations, and then we will also try to go through the IB characteristics. Okay. And then we will also try to go through the power dissipation topic. Second order effects we will see some other time. We'll go through power dissipations. And if time permits, we will try to go through the inverter operations and then your CMOS circuits. So how do you design a circuit and for a given equation? And if a circuit was given, how do you identify what is the equation or probably the Boolean equation? Okay, and all of that. Okay, so let's get started. Uh, okay, MOSFET. So we have gone through basics about MOSFETs. Um, it's basically a four-terminal device, and which is basically nothing but your the source, drain, gate, and bulk. So we always draw a transistor symbol like this. So this is going to be your gate, and say this is going to be a source, and this is going to be your drain, and your bulk would be something like this. Okay, so people call it bulk, or it could be something called substrate. Okay, and source is basically the source of energy. You can call it like either it could be VDD or VSS, and drain is the terminal which is being controlled. Okay, and gate is the terminal which we control it in total. So it's basically you apply something. So gate acts as a kind of the switch. Okay, and bulk is something that it could be your p-type substrate. Okay, or if it is a CMOS kind of thing where you will have a n well also. Okay, so when you say this bulk or substrate, people call it bulk. Okay, or substrate. Okay, or well tapping, well tap. Okay, now this would be for NMOS, we always connect it to ground. So the bulb would be always connected to ground in case of NMOS. VSS in case of NMOS, and VDD in case of PMOS. Okay. Now you also know, we have discussed that there are two types of MOSFET types. So one is enhancement MOSFET, and another one is a depletion. Where in case of enhancement, we try to apply a voltage, and if that voltage is greater than your VT, there's nothing but your threshold voltage. And when the gate voltage is higher than the threshold voltage, the transistor actually operates, or say transistor is on. And coming to the depletion, by default it is on, and whenever you wanted to turn it off, you apply a voltage here. So this, in this case, it is default is off, and you make it on by applying a voltage at the gate. In case of depletion, by default it is on. If you wanted to turn it off, apply a voltage at the gate. Okay, so these two are the types of MOSFETs, and which one we use, in industry, or probably in our product development, and or any kind of research and etc. So we always use enhancement type. Okay, because we always try to control things. It is not like by default you let the things on and you control it, whenever you want. Not the not that way. This is something whenever you want it, that time you turn it on. This is a kind of device that we actually prefer. Now, coming to the what are the different types of enhancement inside this, right? If you look at, so you have NMOS and you have PMOS. So NMOS is basically electrons are majority carrier and holes are minority carriers. Okay. Now in case of PMOS, holes are majority carriers and electrons are minority carriers. So now having said this, which is going to be faster among these two? So NMOS is going to be faster always compared to your PMOS. Okay. For a given same, for the same size. Okay. Now, so when you talk about a transistor, there are two parameters that that's very very important. There are two things. So one is like basically W, and the second one is kind of the length, W by L. Okay, so W is nothing but width of the transistor, and this L is nothing but your gate length. Okay, and when you say a gate length, it is the distance between. Okay, so before we go there, look at this particular picture. Okay, this particular picture. Now, this is how your cross-sectional view would be or look like. Now, see, this is your P-type substrate, and this is going to be a source, and this is going to be your say drain. Now, so this is kind of P-type substrate or P-type body. Now, this is going to be your N-type. Okay, and this is going to be also kind of say N-type. And when you say N-type, now this basically forms a kind of NMOS. Now, the distance between these two, so it's basically on top of this is what we call it a kind of the gate. Okay. Now remember, the distance between the source and the drain, this is what we call it L. This is what we call it L. That's basically the gate length. Now the same thing, it's kind of the 3D structure here. Okay, so you see this L, this is nothing but your gate length. And this, if you look at here, this is something that we call it as a width, transistor width. Now remember, your overall transistor delay, okay, so it's something that we call it propagation delay, that is basically depending on your W and L. So, so when your W increases, okay, your delay decreases. And when your L increases, or basically say, let's say if L decreases, your delay decreases. So it is basically L is directly proportional to your delay is directly proportional to your L, and whereas in case of W, the delay is inversely proportional to your W. Okay. Now, higher the W, you will be able to charge, or probably this particular uh, node, say this drain would be charged either up to VDD level or VSS level quickly. So because of you having a bigger W. Okay. Now this would actually bring down your overall the delay. So any question here? This we have already discussed last week. I think we spent good amount of time, but just a quick recap that I wanted to go through. We'll give you a minute and you can ask if you have questions. Okay, moving on to the next slide. Okay, now remember, we talk about a couple of things, which is something that we call it gate voltage and the drain voltage and the source voltage. And when we say VGS, that means it is always VG minus VS. VGD means it's gate voltage minus drain voltage, and VDS, VD minus VS. Okay, so these are all some things that would be used in these, equations. And as I told, we are not interested in, uh, mugging over by hurting the equations. Okay, you just need to understand the concept of how a transistor is basically operates. Now, as I told you, NMOS body is basically grounded, so it's nothing but your bulk. Okay, it is always at VSS. Okay, and remember, you are assuming that it's going to be at VSS, ground potential. So this is your, transistor cross-sectional view. Okay. Now this is what we assume it to be at ground potential. Now remember, the if in this case your VT, okay, so your VT basically depends on the assumption that you are making. So imagine if this is not at zero. Ideally, if it is zero, then your whatever the regular VT that is, applicable for this transistor would be, same. Now imagine if it is kind of gets into say minus or say zero point zero 0.01 volt. If it becomes positive, what happens to your VT? Okay, and if it is becomes negative, what happens to your VT? Okay, so this is something that you can take it as a homework. Go and figure out what happens to your VT when the bulk potential changes. Okay, you can take this as a homework. So what happens to your VT when your bulk potential basically, changes? So we assume it to be at ground potential, but sometimes it might, be a different potential. Now this is something that we call it body effect. Okay, so there's something that we call it body effect. So this is one of the second order effects which you would really need to know. So go and spend some time this week, and this would actually help you to understand how your threshold voltage varies with respect to your body voltage. Now, if you guys look at, right, why am I telling you this? There is some topic or methodology called back bias. Okay, there is something called back bias or body bias. So if you know this concept, it would be easy for you to understand what is the meaning of this. Okay, now let's move on to the next one. So there are three modes of operations in MOSFETs. So basically, when you say cutoff, the first mode is cutoff. So it's basically your gate voltage is basically less than VT. If you look at here, this is basically less than VT. And when this is the scenario, it is said to be in cutoff. And when you say cutoff, the transistor is said to be in off mode. We call it because kind of, it's kind of off, because you have the gate supply is not crossed the threshold voltage. That means you are not expecting the transistor to be turned on. Okay, so that is the off state. And the next one is basically a linear. So when you say linear, your gate voltage is greater than your threshold voltage. Okay, but your drain voltage is lesser than this particular condition. Okay, so VDS is lesser than or equal to VGS minus VT. Okay, now if this condition satisfies, then it is called linear. And the next one is basically something called saturation. When you say saturation, it is VGS minus VT. Sorry, VGS is greater than VT. Okay, this is a condition for operation. The transistor is said to be in operation. Now remember this. Here you have a less than or equal to. Now this is something that greater than VGS minus VT. Now when this condition becomes true or valid, your transistor is said to be in saturation mode. Okay. Now the important thing for us here is something called IDS, the drain current, ID. Okay, drain current. And we say, theoretically it is going to be say zero, but it will not be zero in the ideal case. Okay. And the IDS in case of linear is something, are expressed in the form of this equation. And as I told, I'm not looking at you solving this equation and all, but understand that this what condition your transistors are going to be operating. That's going to help you. Okay, so this is something that you should know. This is something that you should know. But this equation, which I don't need you to sit and muck it up. Okay. Now let's move on to detailed explanation of say cutoff, linear, and saturation. Any question on this slide? Okay, moving on. Please just give me a minute. I'll just bring some water. Now, the first mode, right? If you look at, can you guys hear me? Confirm. Yeah. Okay, great. So the first mode is basically cut off. Now look at the cross-sectional view of this transistor, where this is your say source, and this is your gate, the drain, and this is your gate. Now, as I said, this is basically a p-type body where you have all the kind of holes scattered everywhere. Okay, and there is no channel that is kind of formed. There is, and it's basically kind of there is nothing. Now if your VGS is less than VT, okay, if your gate supply is less than VT, there will not be any kind of channel that is being formed here. So you will not be, you will not see any kind of, current have, traveling over here. Okay. Now, so this is what we call it, kind of, the cutoff mode. So VGS minus VT, there is no channel formed. Okay. And the next one is your say linear or active region. Now remember, so this is VGS is greater than VT. Okay. Now your channel is basically kind of formed because of this condition. VGS is greater than VT. This channel is kind of formed here, and the holes are being pushed away. Okay. See here, if you look at in the first picture, all the holes that is kind of acting as a kind of a barrier. Now there's those all those holes are kind of pushed down, and now there is a passage that is basically created now. Okay. Now, so this basically makes your transistor kind of say turns on, or say on condition. Now remember, your VDS is basically less than or equal to VGS minus VT. So it's basically, now look at, say this is your kind of big water tank. Now this is a kind of pipe, the tap that you turned it on. Now this is kind of a bucket which is kind of filled, getting filled. Okay, and till your bucket is say 70% full. Now this is the condition. Now say your bucket is kind of almost full. Now that would be kind of the saturation thing. Now look at this. So your ID is basically varies, okay, and your VDS also kind of increases. Your VDS is continuously increases in this case. So your transistor is on, charges are flowing here, and then your this node voltage is kind of getting increased. Okay, and now this is something that we call it linear mode. So now if you look at in this case, your IDS is increases with gate voltage. Okay, remember IDS increases with gate voltage, and it is basically we can call it like kind of it's similar to a linear resistor. Now the third one is something that we call it saturation. Now if you look at, right, so in our digital board we either operate in cutoff. Okay, see any kind of digital chips, it could be either it's called cutoff or we call it saturation. So we operate only, we preferably operate in these two modes, and linear is something that would be used by the analog guys, analog and mixed signal guys. Okay, analog and mixed signal. Okay, and we don't prefer because there are a lot of things that comes into picture, and any kind of say PLL or ADC, DAC, and your many other custom circuits are designed custom way, in a separate, focused only on the uh, the IP, based on the IP spec, and anything that you have to do with something like analog and mixed signal category, they all would pretty much operate in the linear mode. Okay, now moving on to the saturation topic. Now your channel which is kind of formed in the past. Okay, now it was like this before. Say the channel was say something like this. Okay, now when this condition is met, VDS is greater than VGS minus VT. Now that the channel basically gets pinched off. The channel gets pinched off. The channel gets broken. It's not broken. We call it pinch off. Remember this word. It's a pinch off. So that means what? Your current is independent of your VDS, irrespective of your drain voltage. The current would be basically current would be independent of your VDS, and we call this as a kind of current saturate, and then this is what we call it kind of a current source. And if you look at this particular IV characteristics, so this is what a very very important characteristics thing that you should be knowing first, because sometimes you would be asked in interviews. So how can you explain how a MOS operates, and then explain it with IV characteristics and etc. Now, so whatever that we have discussed till now, say cutoff, okay, linear, and saturation. Okay, so these three modes we will try to put it in this picture. Okay, now what is the criteria or what is the ID at, in case of cutoff? So ID is approximately 0 because it is off condition. So it is going to be approximately 0. Now that means this is your ID, the y axis is your ID, and this is going to be your VDS. It's a drain voltage. Remember this, both of them are, one is drain current and another one is a drain voltage. Now cutoff. So ID is irrespective of whatever the scenario is, your cutoff is going to be, your ID is going to be kind of zero. So now this is the area where we call it kind of, cutoff. Though, looking at, this particular, equation, right, it is kind of zero, but it will not be zero completely. There would be some, leakage kind of things where we would treat it like kind of, a static power. Now, so this cutoff region is say, it is going to be say something like this. Now, whatever that we discussed, remember your ID is zero, cutoff, the transistor is off, and your ID is going to be zero. Now, when ID is zero, so this is the area the transistor would operate in. Okay. Now, the next one is your linear. Now, what did we discuss? Your IDS increases with VDS. So that means you just draw this particular, things. For each VGS, gate supply voltage, this is how it is going to be. So charging, and then it becomes constant, and then say this is going to be kind of, again. So now if you look at this all things, right, see, your linear is going to be kind of, this is the area where we say the transistor is said to be in linear mode. Okay. Now just try to recollect this particular statement. Your IDS increases and your VDS also kind of, increasing. So both of them are increasing. Okay. Now you need to understand that, both ID and as well as VDS are increasing. Now look at this whole thing, irrespective of the things. Your ID is increasing and as well as your VDS. Okay. Now this is condition. This is a condition for your linear. Okay. This is a condition for your linear. Now remember, the third one is basically the saturation, and saturation is basically your independent of your, basically your ID is independent of your VDS. That means what? Your ID is kind of constant. See, what is this meaning? Saturates. Your current is becoming constant, and that is basically, irrespective of your VDS, whatever the VDS supply voltage or VDS voltages. Now, when you say current is kind of, constant, this is what it is. Your current, your VDS is kind of, increasing. See, even if let it be 4 volt or 6 volt or 10 volt or whatever volt it is. Once the channel pinches off, your current becomes basically constant. Okay, your current becomes constant, and this particular, phenomena or the region is basically we call it saturation region. Okay, so if you are able to explain all the three modes along with this IV characteristics waveforms, this definitely they will know you, they will not reject you for sure. So any question here? uh okay, I can explain it. Now, the condition for turning on your VDS, the transistor is basically VGS greater than VT. So this is a basic condition. If this condition is not met, see if it is less than VT, then it is kind of off. Now, so VGS is greater than VT, that means it is turned on. Now you need to know whether it is operating in linear mode or saturation mode. Okay, linear mode or saturation mode. Now this is going to be identified. We can, we will be able to identify based on this equation. See, if VDS is basically less than or equal to VGS minus VT. Okay, this is going to be, we call it like kind of linear mode. Linear mode. Okay. Now, when during the linear mode, your channel is very well intact. So the whole channel is basically going to be very well intact. There are no issue at all. It would be just continuous channel. Now the third phenomenon is called saturation. When your VDS is greater than VGS minus VT. Okay. Now that means if when this condition is met, that is the time the channel basically is we call it pinch off. So if you look at here, this channel is basically now starts pinching off. Okay. Now this, when this happens, your current becomes constant, irrespective of your supply voltage, the drain supply. Your current becomes constant. That is what you should remember. So if you are able to understand the three modes of operation, and if you are able to understand the IV characteristics, you are pretty much there. Okay. And when you say saturation, that means as I said, your current is constant, and we call that scenario or that phenomenon is something that we call it a current source. Did I answer your question? Okay. Yes. Yeah, that's what I'm saying. No, it is say when this condition, say simple, right? Now VDD is here. Let's do this. No, let me just try to help you guys so that like you guys would be able to understand. Say for example, your VDD supply is say 5 volt, and your VT is say zero point 0.7 volt. Okay. Now this is your transistor. Say this is your transistor, and say this is your 5 volt, and say this basically your gate, and say this is your drain. Okay, so this is basically your NMOS. Now, what is going to be the drain supply? Now, drain voltage, assuming if VG is less than VT, transistor is said to be in off condition, so there is no problem. Okay. Now, when the gate supply is greater than VT, what will happen to your VD? Anyone? So you need to understand that your VD is going to be VDD minus VT. What is going to be the voltage here? Now, so 4.3 volt. Now, the moment the condition is getting, so remember now VDS is less than or equal to VGS minus VT. Your gate supply and minus VT, if it is condition of this, remember you guys have to understand one thing. You don't need to get into this more too much of equations. Say this is your inverter and this is your another inverter. Now you give your signal here, say something like this. Now your output is going to be falling. Okay. Now this fall goes here. Now this transition, whatever that you see here, it gets degraded. Okay. This transition is going to be very sharp here, but when it travels through this wire, this is going to get degraded. Now this takes this signal, the degraded signal, and it is going to be kind of you know boosting the signal quality and pushing it out. And again, it travels through the wire, and then when it is reaching say and gate. Now here it is going to be kind of, it is going to kind of, degrade. So this is the kind of, behavior that you would see. Now your VGS, that's nothing but your gate supply. Okay, the gate supply. You can see this, right? Here. VGS meaning VG minus VS. Okay. So this condition, the moment this condition is satisfied, the channel automatically pinches off. Okay, so that's a basic mass thing. You don't need to go and do kind of, research and figure out why it is happening and what is the reason behind all this. These are all something that you really don't need to worry about it. But if you know the basics of mass operation, that is more than enough. If you really wanted to go and learn how this thing all happens, there is a book called MOSFET modeling, mass modeling. I think TCDVS is the author. If you guys wanted to go and learn in depth, you can go and take that book, and the PDF is available. You can download and go through it. But you are not into research here in physical design. You are into you're going to work in the physical design domain, where you would be pretty much implementing the designs and solving the challenges. Okay, but these are all the basic things where you should be knowing, okay, how mass operates, and when it comes to say inverter, how do we design an inverter, how do we design a buffer, and all of that. Augustine, in case if you really have not understood, you can get back to me offline. I'll try to help you. But uh, if you were able to understand what is basically meaning of channel pinch off, that should be good enough. So when this condition satisfies, your channel gets kind of pinches off. If not, then it would be kind of, the channel would be continuous. So you can see in this particular picture here, you see this, the channel is kind of very well intact. You see, because the condition is not satisfied yet. Okay, all right. Moving on to the next slide. So, the second order effects we will see sometime next week. Let's quickly go over the power dissipation now. Now, remember, any kind of switching that happens, you will have to the transistor basically consumes power, and that power gets converted into a heat energy. Okay, the switching generates heat. Now if you guys look at, right, when you are playing a high-end games, what happens to your mobile phone? It becomes heat, right? It becomes hot, and then you would actually sometimes some apps might misbehave in case in case of the temperature is very high. So your switching, the transistor switching basically converts electrical energy into heat. Okay, and now what is the meaning of switching? Let's try to understand. Say you have a inverter, you give 0 and you get 1 here. Now this is something that we call it switching. Okay, this is something that we call it as switching, or vice versa. Okay, you give 1 here and it becomes 0. Now the whole thing, right, the internal transistors basically are conducting. It could be either PMOS and an NMOS. Okay, we will talk about that, the whole, what is the meaning of PMOS and what is the meaning of NMOS and everything in a while. Now, before that, let's quickly finish the power dissipation topic. Okay. So since we are going to focus mainly on CMOS side, let's quickly cover CMOS. Then we coming to the power. Will it make sense? Okay. Let's try to understand CMOS first. So we discussed about, so what are the different types of families, logic families in with MOSFETs? So logic families. Okay. So the first thing is basically there is something called pseudo NMOS. Pseudo NMOS. Okay. And the next one is basically there is something called past transistors. Past transistors. And you will also have something called transmission gate. Okay. Transmission gate. And you will also have something called domino logic. Okay. And you will also have something called CMOS. Okay. Now, which is the one that is used in by the folks? It is basically the CMOS is the technology that we use, because each of this, right, say pseudo NMOS or post transistors or transmission gate or domino logic, they all having kind of more the disadvantage than your advantage. But in case of CMOS, it gives you that the advantage, a fair advantage than all these families. Now, so let's understand one thing here. So you guys know there is a NMOS, okay, and there is a PMOS. Say for example, this is your source, and say this is your drain, and this is your gate. Now, as I said, say your VDD is zero, say 5 volt, and your VSS is basically 0 volt, and your VT is zero point 0.7 volt. Okay, now I want you to plot the waveform. So this is the kind of levels. Okay, say this is your 0 volt and this is your 5 volt. Now you guys know that what is the meaning of logic 0 and logic 1. So it is basically when you say logic 0, it is exactly at 0 volt, and when you say logic 1, it is at exactly at say VDD volt, or we call it say in this case 5 volt. Now the perfect thing could be, this is going to be a perfect waveform that I would be interested in. Okay, do you guys see that it is starts with, when you say logic 0, it is kind of 0, and when it is logic 1, it is exactly at or similar to your VDD, which is called 5 volt. Okay, now this is what preferred by the industry folks. Now let's go and take a look at what will happen if you use only NMOS. Okay, can someone tell me what will happen to your this one? Now assume, remember, what did we say? So this is your VDD. Okay, now your formula is VDD minus VT. VDD minus VT. Now what is it going to be in case of this VDD? What is it going to be? It is going to be say at 0. Okay, but it is going to be kind of say 4.3 volt. Is it reaching up to 5 volt here? What is this? Take this values, apply that in this formula. What is it going to be? 4.3 volt only. It is not going to be equivalent to 5 volt. Now this is something that we call it weak one. Okay. Now with the NMOS. Now let's apply the same thing when this is something that 0. When you connect the source to 0, now what happens? Apply the value here. So it is going to be, since it is kind of modulus, it is going to be exactly kind of 0. Okay, so in case of NMOS, right? So when you connect your source to zero and you make it operate, it is going to give you exactly the level that you wanted. Okay, so this is something that we call it strong one. Sorry, strong zero. It is strong zero. So this guy is basically NMOS. Okay, so it's called weak one and strong zero. Now, what about your PMOS? So this is also kind of, say, it is going to be VDD plus VT. Okay, same more or less. Now, say this is 5 volt. Now, what will happen to your this particular thing? It cannot go beyond that. So it would be always capped at, say, 5 volt only. Now, your VDD is going to give you always the logic one, the complete logic one levels. Okay, so because of the nature, it's minus, see here it is minus VT and here it is kind of, plus VT, but it is going to be 5.7. That's how it is going to be, but it cannot go beyond 5. So 5 is what the max thing. Now this is going to be at, see, exactly 5. Now what is this called? This is called strong 1. Okay, now remember, make this as a kind of, zero. Now what is going to be the drain voltage or the drain potential? It is going to be zero point 0.7 volt. Okay, because 0 plus zero point 0.7 volt, it is going to be zero point 0.7 volt. Okay, so it is not going to be kind of, reach all the way till here, this one. Okay, it is going to stay something like this. So this is something that we call it V0. Okay, now look at this. Both, NMOS and PMOS case, there is they have something called weak one and strong zero, and this guy is having a strong one and weak zero. Now, what we do is we actually go and club it. Okay, now look at this. The top one we try to use PMOS so that this would take care of your logic one. Okay, and bottom one we try to use NMOS, and that would take care of your logic 0 because your strong 1 and strong 0. Okay, now this is the main reason that we wanted to have both the side the strong. So that's what I said, right? I wanted to have exactly, say, VSS, say this VDD. This is going to be the desired signal. Now this desired signal you will get when you add both PMOS and an NMOS in the circuit, because PMOS gives you strong 1 and NMOS gives you strong 0, and that is the reason we use PMOS on the top and NMOS at the bottom. Any question here on the strong 0 and weak 0, strong 1 and weak 1? This is very important thing. So without you having an idea, you will not be able to answer why are we going for CMOS, complementary MOS. And we always use PMOS on the top and NMOS on the bottom, just because we wanted to have the strong one. We want to take advantage of the PMOS, so that you will get strong one. And you also, give me a minute. Let me just finish. So you use the NMOS at the bottom. That would actually give you a strong zero. So if you really wanted to achieve, say, this kind of waveform, the signals, then you should always use PMOS at the top and NMOS at the bottom. Yeah, someone was asking something. Please go ahead. Yeah, right. Yes, I'm not getting. What is it? Which one is? There is no depletion mode. There is no depletion mode. We use, as I clearly told, we use only enhancement type MOSFET. There is no depletion mode that we use in digital circuits. Okay. Yeah. Any other questions? Okay. Now you guys learned your PMOS, I mean, CMOS. Yeah, go ahead. No, it will achieve weak one and strong, week one and week zero, so which is not preferred. That's There's going to be, say, something like this. See, give me a minute. Let me just explain you. Now, if you use PMOS in the bottom, NMOS at the top, what will happen is your waveform will be always, say, something like this. It will not go either here on the top complete or at the bottom side complete. Now, this is not what we want. We want the signal to be kind of, we want the signal to be something like this. Okay. Did I answer your question? So if you use NMOS on the top and PMOS on the bottom, you will end up with waveform which is going to be, say, something like this, and which is basically going to give you, say, kind of weak zero, because it is not completely zero, and it is also going to be kind of weak one because it is not completely up to VDD level. So this is something that we don't usually prefer in the industry. Yes. Yes. No. No. Wait. uh, your NMOS and PMOS, if you look at, let me just explain you that. Okay, now remember, when we give one, when we give, say, logic one gear, now what will happen is this NMOS would be turned on, because NMOS would be VGS is basically, see, VGS is greater than VT in this case. Now this is going to be turned on. Now this node would be completely discharged. So whatever this Z is there, no, it would be completely discharged. Now, what is this meaning? Z would be zero potential because it is being completely whatever the value that is stored over here. This would be completely discharged. Okay. Now, when you give, now, so in this case, only this is going to be on and this is going to be off. Okay. This is going to be on and this is going to be off. And in case of zero, what will happen is this would be on and this would be kind of off. Okay, so that is how the PMOS and NMOS operates. NMOS operates when it is logic 1 and PMOS operates when it is logic 0. Did I answer your question, Bala? Forget about depletion. There is no depletion. You are only in enhancement type, in which you will have to apply a voltage to make the transistor work, or to turn on the transistor you have to apply a certain voltage at the gate. So there is no depletion. That is just in terms of concept I brought in and I told you, but there is nothing called, we don't use the depletion mode anywhere in our designs. Okay, yeah. Now let's solve a quick problem. Okay, so case 1. And what is going to be your voltage here, and case 2. Now what is going to be the voltage here, and case 3. What is going to be the voltage here? I'll give you a minute, and you guys know that VDD minus VT. Okay, now this whole thing is something that we call it pos transistor logic. Pos transistor logic. Case 1 and okay. Tell me the numbers. Tell me the numbers. Tell me the. Okay, so let's wait for. So two people have said the second case 2.9 volt, and one, you are saying 4.3. So okay, so let me just. So the answer that you gave was kind of 4.3 volt, and say this 2.9 volt, and you are saying this is also 4.3 volt. So this is two persons, and this is again two persons, and this only one person gave answer at this moment. Only two people have answered. What about others? I gave you the equation already. You need to just apply your, basics, and then you should be able to answer the question. Okay, so this have got, so plus one. I see. Okay, so there are four people. I think there are five plus people. Done. Okay. Now let's discuss the answers. So this particular case, 4.3 is correct because it is straightforward. So you apply VDD, which is 5 volt, and minus VT, which is zero point 0.7. So it is going to be 4.3 volt. So this answer is perfect. Okay. Now remember, this is something like kind of, seriously, connected and kind of, cascaded. Let's say we call it kind of, series. So basically, drain connecting to source, and again drain connecting to source. So you need to first understand that, see, this is your source, and this is going to be your drain, and this drain acts as a source for this transistor, and this becomes your drain, and this becomes your source, and this becomes your drain. Now, so the first node supply is going to be kind of, 4.3 volt. Apply this equation. Now this 4.3 is going to become your new VDD here. Now this is going to be kind of, 3 point change. say 3 point how much 6. Okay, now this is going to be kind of 3.6 minus zero point 0.7 VT. It is going to be 2.9. Okay, this is the right answer. Now coming to this one, so assuming your this is also 5 volt, this also 5 volt. Now what is it going to be? So assume all the gates are driven by 5 volt. Okay, see this is also 5 volt, and all this are all 5 volt, and this also kind of 5 volt. Some folks have said like kind of 0 or probably not triggered and etc. Assume now it's a 5 volt. What is going to be your the final voltage? Now understand, the moment it is beyond VT, the transistor turns on and it starts conducting, and as usual your VDD minus VT, it is going to be kind of 4.3 volt. Now this 4.3 goes here, so it's basically greater than VT. Now this transistor starts conducting, and this is going to be again kind of 4.3 because your VDD is kind of 5 volt only. Okay, now so this is also kind of 4.3, and your VDD here is 5 volt. Now your output is again going to be see 4.3 volt. Okay, so this is how the voltage levels when you use POS transistors. Okay, now irrespective of any case, it is not helping you to get 5 volt. Okay, so this is the main reason that we don't prefer POS transistors in our designs. And remember, this kind of problems, whatever that I have given you now, these are all some things that I usually ask in the written tests, or basically companies would ask in the written tests. Okay, I'll just give you a minute to ask questions if any. Okay, moving on. Now, so we talked about POS transistors and the how they operate and why we don't prefer. Now, the next thing is here something called transmission gate. Transmission gate. Okay, now, so when you say transmission gate, that is combination of both PMOS and an NMOS. You need to just remember. So you have your signal. This is going to be your signal. Say this is your A, and this is going to be your A bar. Okay. Now, so this is going to be your input, and this is going to be your say output. Okay. Now remember, the transmission gate will help you to have reaching here the waveform requirement. So it is kind of VDD, and I say this kind of VSS. Okay, but remember one thing: if there is any kind of noise, so there is no problem with the logic levels in case of the transmission gate. So we are good in terms of logic levels. Okay, VDD and VSS, but there is a problem. Now, what will happen if you get a glitch here? Can anyone think about it? If there is a glitch, will this be suppressed or will this be propagated further? In case of transmission gate and in case of regular, mass. So assume, say this is a kind of thing, and whereas this is in the input stage. Now, which is going to be better in terms of, say, this kind of noise? Now, have you heard about something called noise margin? I'm sure everyone would have heard about it because you would have gone through the data sheet of any kind of IC, they would have mentioned like something like, say, noise margin. Sorry, someone was asking something. Bala, I think it was you. Okay. So case one and case two, which is going to be better from a noise margin perspective? Okay, let's go for quick voting. So which is going to be benefit in terms of noise margin? Which one would you guys go for it? Quick, you can type one or two. Okay, so you would go with two. Okay, what about others? So one plus one. What about others? Okay, so Priyanka says type one, and then next we have a lot of people, but I got only three answers. Good morning, wake up. Guys, I need you to type your answer. So I'm asking, so there is a circuit something like this, and there is a circuit something like this. Now both of them are having an input spike. Okay, there is a noise on the input. Now, from a noise margin perspective, which is going to be produce, I am not asking you any kind of explanation. You need to choose either one or two, and then we will talk about it. So, okay, so two. Okay, so produce, I am going to put one because you are committing yourself for one towards one, and so this is two plus two, and Savin one. Aruna is one. Arun and others. So we have got only eight people. That's fine. Even if you're wrong, you need to take a stand when I'm giving you. Okay. So Shravani says one. Kalimani is one. Okay. I think we have one coming as a majority. Okay. So since this one is kind of majority, okay, but the answer one is totally wrong. Now remember, if in case of transmission gate, you know, if there is a kind of glitch, what will happen to your output? It would get amplified much better. It would become a bigger one because of your, the structure. It would get amplified. Okay. But in case of this, likely that it might get suppressed. Okay. Likely that this might get suppressed. So from noise margin perspective, we always go with this kind of style. So when I say this, meaning you have controlling your gate. You controlling your gate is what we prefer, not like the noise getting propagated to your the source, and then that is reflecting in the drain and etc. So we won't use transmission gate just because it is having a poor noise margin. That is the main reason. Okay. Any questions on the transmission gate? So we don't use transmission gate also in our regular designs just because that is having a poor noise margin. Okay, moving on to the next one. So now, so each and every and families, right? So we have some or other issues. So that is the main reason we go for something called CMOS. Okay, so PMOS on the top. Okay, it is, we call it pull up network. Okay, and NMOS at the bottom, pull down network. Okay, now if you look at in this case, your gate is the one which is being controlled. So your PMOS, again, the gate controls your MOSes. Now remember, even if you go to the next stages, say something like this. Now, what is the circuit basically? This is something that, one inverter driving another one, as simple as that. So that means what? You are basically connecting one inverter to another inverter. Basically, one inverter is driving another one. So your PMOS, basically your CMOS structure, right? It is like kind of, this is something that we call it pull-up network, because the logic would be pulled to high because of this MOS trans turning on, and these guys are going to contribute towards your pull down at basically zero. Okay, so that is the main reason we prefer PMOS, because it is giving you both strong one and strong zero, and we don't see any kind of weak values, and it is easy to implement in terms of when it comes to this overall circuit design and implementation. Okay, all right. So moving on to the power dissipation. Okay, so there are two types of power dissipation. One is basically there's something called static power, and then say second one is kind of dynamic power. Now, what is this? Assume you have your phone, you have charged it completely 100%, and you turn off your data and all Wi-Fi, and no, even you can put your phone in your airplane mode. Now, leave that phone for ideally for say 1 hour. Now, after 1 hour, say before 1 hour, 100% of your battery. Now, after 1 hour, you would see kind of 85 to 90% of the battery. You have not used your phone for any kind of calling or any kind of gaming. Basically, you have not done anything with your phone last say 1 hour. Now, your battery would have got drained, or probably the supply, the storage, right? Now the battery would have you know somewhere around 85 to 90%. Now, what is this meaning? Because though you have not used your phone, but still there is a power consumption. That is nothing but your static power. That is nothing but your static power. Okay. Now, the static power is basically happens due to these things. So, first thing is basically sub-threshold conduction. Okay, sub-threshold leakage or sub-threshold conduction, people call it. Now, what is this meaning is you have your, now you guys know that the channel is not formed when the transistor is said to be in off condition. Okay, but that doesn't mean that there will not be any kind of leakage. So there would be some leakage because of your subthreshold conduction. So we, though we call ID is zero in cutoff, but ID will not be zero. because of your leakage. So leakage is meaning, say simple, right? You, irrespective of whether you use it or not, there is a power consumption. That is basically that we call it your leakage power. Okay. Now, what are the different components? So one is subthreshold leakage, okay, and then reverse bias diode. Now, if you look at, say this is your P type, and say this is your N type. Okay. Now, if you look at the structure of diode, this is how it is going to be. Correct. This is how it is going to be. Now, this is something that we call it a kind of, say, P and N. It's a reverse bias diode leakage. Okay. And the next one is basically your DIBL and channel punch through, some other leakages, hot carrier, and these are all, comes under or probably, contribute to the static power numbers. Okay. So any question on static power? Now remember, your power is equal to P static plus P dynamic. Okay. Now when you say P static, okay, your VDD, okay, that is going to be your regular VDD. Okay, so this is your VDD. Now the important thing is into your I leakage current. Okay, so this is the formula for your static power consumption. Okay, this is a formula for your static power consumption. Okay, now when it comes to dynamic, okay, there are two things. One is P short circuit and then plus switching, P switching power. Now look at these two things. One is short circuit and another one is switching power. Now remember, there is always output capacitance. So any circuit. Now look at this. So this node is going to have something called the CL, that is an output capacitance or load capacitance. So CL is basically, now there is a wire which is connecting all of these things. So there is a wire which is being connected. Okay, so there is a wire which is being connected. Right now, that means C net. So there is a capacitance because of the load, the wire. And then the next one is, now there is a gate capacitance. You guys know that, right? Say for example, now, okay, now if you look at, say there is a kind of capacitance, you know structure. Now look at here. So there is a PMOS capacitance and there is a NMOS capacitance, and then this together, both of that together, put it like kind of, the input I. Now the same case here. See, there is a PMOS transistor and NMOS transistor, and your pin is basically I. So your I, the pin capacitance, okay, it's basically a gate capacitance, and that, so this is the formula that would be used to calculate your load capacitance. Okay. Now let's quickly go and understand what is the meaning of charging and discharging. Okay, let's take this inverter for example. Okay. Now the moment you give zero here, which is turns on, which transistor turns on. So when you give zero here, this transistor turns on. Okay, and it charges up to, see, logic 1, complete VDD. Now when you give 1, what happens? This transistor turns on and there is a path to ground. Now this is being completely pulled down to 0. Okay, is it clear? Now this charging and discharging is called switching. Okay, charging and discharging, and then the power that is dissipated during this charging and discharging of this capacitance, it's called switching power. It's called switching power. Now this particular component is something that comes under dynamic, because when you're playing games or when you're making the transistor work, that is where you will have your switching power coming into picture. 0 to 1 it is switching, and 1 to 0 it is switching. Okay, so any question on switching power? Yes. Okay, so now uh, charging capacitor is equal to what? Now, no. See, it is, we call it output capacitor or load capacitor. Now, see, you need to understand that is just a name that we just called it as extra capacitor. But now remember, this is not you are adding intentionally. So this capacitor that you are having, that is not added intentionally. Okay, because it is by the structure of your overall mass, it is being automatically formed. These capacitances, now the question, probably I would answer your question in a different way. So these are all something we call it parasitic. We call it parasitic resistance and capacitance. Okay, when we say parasitic, there are two components. Parasitic extraction, what we call it. And so there are two components. One is resistance and capacitance. We don't deal with inductance. Okay. Now, when you say the CL, it is, so your load is basically going to be depending on the number of fan outs and how long this wire is actually routed. Okay, so this is nothing but assuming your, say, AND gate, it is going to an AND gate here, an AND gate. Now look at here, you give 0. Now what will happen to this AND gate, the NAND gate over here? What will be the input to this NAND gate? So when you give 0, your PMOS turns on and it charges your cap. Now this cap getting charged, meaning this node is basically pulled to 1. This node is pulled to 1. Okay, this node is pulled to logic 1. So that is how you are basically, switching, turning on the transistor and managing the states. Now imagine if you are giving 0 here, say you are giving 0, sorry, 1 here. Now what will happen? This NMOS would turn on, and all these fan outs, okay, they all would be kind of, the node would be discharged to 0. So you're basically say, assume you have something like this, you would come to say something like this. Okay, now in case of charging, it is going to be say something like this. Okay, now remember this load cap, whatever that I am drawing, this load cap, it is not that I am intentionally adding it. Let me repeat this. I am not intentionally adding it, but it is actually formed when you manufacture your devices, when you manufacture your IC. Okay, so now it is not that you see the next node, how you make it logic 1. You are giving 0 here. Now this output becomes 1. Now that output is basically should reflect at this particular place, right? Yes or no? See, now you are giving 0 here, and your output is going to be kind of 1. Now all these fan outs should have what? All this, okay, all these things would be having 1. Now imagine after some time, this would be kind of say changing, the input is changing, and this is kind of becoming 1. Now it would be kind of discharged, so all the things would be kind of discharged to 0. So when you see a load capacitance, it is nothing but your wire capacitance plus C pin. The C pin is nothing but your gate capacitance. It's basically a gate capacitance. So people, don't get confused. Your load cap is not intentionally added, and you have it is all exist, or probably it comes into picture when you manufacture the shapes, and you have to live with that. You cannot avoid. Okay, you have to avoid. You cannot avoid, so you have to live with that. Okay. Okay. Now coming back to our switching power. So during this charging and discharging, no, there is certain power that is consumed. Now that particular thing is called, they comes under. So when charging, this is going to be happening through PMOS, and when discharging happens, something like this. Now this is how the other subsequent nodes. See, you are connecting to now next few things, and from here next few things, and etc. So that is how your whole logics that are being maintained. Now switching power, because of the switching, charging and discharging, the power that is consumed, at that time, so it comes under the switching power. Okay, and the equation for the switching power is something alpha cv squared f. So remember this, it is alpha c, no, alpha cv squared f. So you can call it like p switching. Okay, now, so I want you to go and explore this particular thing. Okay, Now, moving on to the another component that is called short circuit power. What is short circuit power? So you see here there is a short circuit power. Now, just remember this particular thing. Say when your signal is something like this. Okay. Now, during this state, so at the time of state one, it is going to be PMOS is going to be on and this is going to be off. And during this transition two, okay, this is going to go from on to off. Okay, and this is going to be turning out from on to off. Sorry, off to on. And then third, okay, so it is going to be completely off. This is going to be because it is 3 is basically logic 1 and logic 1 for PMOS on the top, which is kind of off, and NMOS would be kind of say on. Now, during this whole process, if you look at the transistor is changing its state. See this during this particular time, from the on to off and off to on during this transition. Okay, during this transition, it would actually turn one would be transitioning from on to off state, and another one is going to be off to on state. Now, during this time, there would be at some point you will have your direct path between VDD and VSS. Okay, so this is something that we call it I short circuit. Okay, there for a fraction of seconds. Now, say so this transition is 300 PS. So this transition is 500 PS. Okay, and assume so there is a short transition, just kind of 150 PS. Now, so this is your homework. I want you to go and figure out which is going to help in terms of your short circuit power. So let's see if you wanted to reduce your short circuit power among these three scenarios, which is going to help you. Okay, note down this. This is a kind of homework for you guys. Okay, now coming back to short circuit. So there would be a fraction of seconds. The power, there would be a direct path between VDD and VSS. Now, during that time, whatever the power that get dissipated during this short period, now that is called short circuit current. Now, your short circuit power meaning it is going to be kind of say VDD into ISC short circuit. So this is going to be your short circuit power, and we have just discussed. So P dynamic is nothing but alpha C V squared F. Okay, and we also have talked about say P static. What is the static is your VDD into I static. Now, so together, so P total. So it is basically P static plus P dynamic. Okay, so now the dynamic is going to be just both together treated as a dynamic power because both say switching power plus your short circuit power. Okay, now this together it's called dynamic. So this is how we actually calculate your total power consumption. So any question? It is basically the switching activity. So whatever the alpha that you're seeing now, so this is basically your switching activity. No, it can be anything. So it can be anything, no? So it can be anywhere from point 1 to 1 or 2. It can be, it can, it can go up to 2. So in a given cycle, how many times it is switching? Say for example, you have a circuit. See, there's a kind of, say three cycle that you're passing. Now this three cycle goes through a, say, logic. Okay. Now, how many times the logic is actually switching? So that is nothing but your switching activity. Okay. Now the C is nothing but your cap. Okay. Parasitics. And then your V squared. So your voltage, you are getting a double benefit when you wanted to touch and reduce it. And then frequency also. Okay. So now the question is, or probably let me give you homework. What are the different ways that you would go and optimize your dynamic power? Because everything is there in this equation. What are the different ways that you would go and optimize your dynamic power? That can be your another question which you can work on later during the weekdays. Okay. Okay. So that sums up the complete power dissipation. Any questions? Okay, great. So this is done now. So let's just spend some quick time in understanding the inverter, how a CMOS inverter operates, and then we will stop the class for today. Okay. Now we guys know that we just discussed that if you give 0, your PMOS turns on and the cap is getting charged. Okay. Now if you give 1 here, what is that going to happen? It is going to kind of whatever the things, the value is there here, it would be discharging. Okay. So now, so when you give 0, your output is basically 1, and when you give 1, output is basically 0. So this is exactly what we call it, a inverter. So when A is 0, PMOS is on, and output Z is charged up to VDD, and which is known as logic 1. And so that's exactly what you're seeing here. 0, you give it as an input and you get output 1. And when A equal to 1, okay, NMOS is on and Z is kind of completely discharged up to the VSS value. So that's something that we call it logic 0. Now this is basically the schematic of your inverter, transistor based schematic for inverter, and this is something that we call it a gate symbol. Okay, gate symbol. Okay. Now this is something that we call it a layout. So this is what, see, when you say inverter or the schematic, end of the day, this is what actually gets manufactured in the foundry. Okay. So you knowing the inverter operation is very, very important. Start analyzing. So you need to draw a circuit like this and start analyzing how the circuit is going to operate. Okay. And for you, the next week homework is I want you to explain the inverter, operations along with this all the waveforms, including your input output waveform. Okay. Now, what I want you to do is for the upcoming week, I want you to understand NAND NOR operation input, and this one is I said input and output relation. So now the inverter, right? So I'll explain you that, but this is going to be a next week assignment where you have to explain about NAND schematic and NOR schematic, and you need to write this condition what is getting turned on when. Okay. Now coming back to the inverter, so there is something called waveform that we always look at it, input output waveform. So it is going to be say V in and V out. And in case if this is the scenario, something like this. Okay. So this is gonna be kind of V out, and say this is gonna be kind of V in. Okay. So this is a kind of waveform that you should understand uh, how the device operates, and you should be able to draw something like this. And now I want you to go back and draw a schematic for both NAND and NOR, and then write the conditions like what is turning on and when, and then submit your assignments. Okay. Okay. So let's stop for today, otherwise it will be too much. This MOSFET or CMOS is something that kind of not many would like it, but so we'll stop here. Next week we will talk about the second order effects, the whole second order effects, and then we will go on design the circuits for a given equation, and then we will talk about layout in the upcoming weeks. Any questions? Okay. What is it? I'm not getting what. Huh? Okay. See, no. Let me tell you what we are talking is a simple MOSFET, which is kind of CMOS based implementation. Other than that, we don't have any other technology that is actually implementable. Floating gate, I never heard of it. I know only there is something called FinFET, GIA FET, multi-bridge FET, and all of that, and CN FET, carbon nanotube FET, and etc. I have no idea. I need to check. But I have no. See, let me tell you, I have never. See, if there would have been a product which I have to design using that, I would have learned it. But now, all these years, I have never heard any kind of product with that kind of technology. Yeah. Okay. Any other question before we sign off? One last question. Okay, all right. So if you have not enrolled for the course, and we have already started, talking about Linux and everything, and we have given you the Linux files and everything. So I hope I have, you are able to, install it. I know Bala have installed it. I know, I think Kalaimani have installed it.